starting to talk about so-called matter waves. Matter waves. And basic idea is if waves show particle properties, particles should also show wave properties. Okay? And this was the first suggested by de Broglie. Oops. This is de Broglie. Matter is also wave. So let's first to be more concrete. Let's start with light. Right? In the case of light, Planck showed E is equal to n times h nu, but let's take n is equal to 1. It's like just h nu. And relativity, or Einstein showed E is equal to or P is equal to E over C. Then if I put this h nu, P is going to be equal to h nu over C. But like our usual equation, lambda times nu is equal to C, then P is equal to lambda is equal to what? Lambda is equal to C over nu. So I can write this like H over C over nu. Then P is equal to H over lambda. Okay. So this relation P is equal to, I can also invert this and say a wavelength of a particle is related to its momentum by H over P, and it was first suggested by de Broglie. Okay. And this is in his honor, this is called de Broglie wavelength. For example, what is P? For relativistic particles, P is equal to gamma mv, right? Then lambda is equal to H over gamma mv. Okay, this looks like mu, this is V. And here gamma is our usual factor, 1 over 1 minus V squared over C squared. So we can calculate, for example, as an example, an electron moving with V is equal to, okay, in my example, 10 to the 7 meter per second. So this is still much less than, V is much less than speed of light, so we can actually use non-relativistic result, which is, we showed, which actually agrees with relativistic result. So the Broglie wavelength, lambda is going to be equal to H over mv. You can also put gamma if you want. And this is going to be order of 10 to the minus 11 meters. Right? Yes?
Can I understand what was significant of this? Like what the Broglie showed?
So the significance is like now we are talking about like billiard balls we are talking about trucks, we are talking about objects we see around, and we claim that they are also waves. And if you ask me what is the wavelength, right? Waves should have wavelengths, and these objects around us, like billiard balls, have wavelengths. Because of this calculation, right? Even for electron, which is like a textbook particle, wavelength turns out to be very tiny, very hard to observe, right? So 10 to the minus 11 is like very small wavelength. So the objects around us, which are matter, we call matter also is a wavelength, but that wavelength is tiny. So that's the significance. So we are like, de Broglie is suggesting that everything is wave, but showing it is not easy, right? That's the message. Any questions? So we'll come to the point of how to detect waves like this. I'll give you a summary of an experiment later. But now I want to ask the following question. So if matter is wave, what is waving? I think I didn't make up this. I think your textbook is using waving, but maybe I imagined a word like this. I apologize in that case. So the point is, for example, sound is oscillations of air, water waves, oscillations or motion of like a liquid. Then in the case of matter wave, what is the oscillating thing? What is doing that?
Radiation that we emit.
But it's like we said, that's the case, for example, in the case of light, right? The oscillation is electromagnetic radiation, we show that. But are you also saying that for the billiard balls, that wave also is like an oscillation of electromagnetic field?
Yes.
Right? Something should go up and down. So I think the answer is no, because that's the case for electromagnetic radiation. But for the matter, as far as we know, there's, right? It's just like it's just something with mass, right? Something should be oscillating back and forth. So any suggestions? Something should be like waving. Time, maybe? You are saying time?
Maybe space-time.
Space-time? Like oscillations of space-time is also something else. Like let's not get into that. There is things like this, but it's called gravity waves. Huh? Nucleus itself is oscillating. Anything you can imagine. Like what is the craziest suggestion you can have in fiction movies? All right. Yes.
Energy.
Energy is oscillating. Energy is conserved, right? It's not something going up and down. I think the reason I want you to think is it is very non-trivial, and I think even today nobody knows what is oscillating. For matter, a wave function is waving, and we call it like this Greek letter psi. So this is our first introduction. So this is a complex. So so this is a wave function. So this is called wave function. So it is a function. First of all, that's a good thing. We know about that. It is complex. So what this means is it has like a real part. Let me call this okay, that x is going to mix with this. Let me call this a real part, which is going to be a function of x, y, z, and t, plus an imaginary part. Let me call this v function, x, y, z, and t. And this I is equal to square root of minus 1. So this is waving for matter waves. Unfortunately, I think we can sit down and argue what wave function is, but as far as I understand, nobody knows what wave function is, and we have to live with this. And because it is complex, psi, because we can't observe complex numbers, right? They don't exist. Psi is unobservable. Unobservable. That would be nice, but that's not the case, right? Actually, imaginary part is also physical, but we cannot observe it. Both real part and imaginary part, they are necessary. Like we give the example, like in, for example, electric and magnetic, like in physics 106, there are certain circuits very hard to solve. But if you write them in terms of complex numbers, right, it's easy to solve, but at the end of the calculation, we take the real parts. There should be nothing complex in like classical physics. Complex numbers is like, just like a machinery we use in classical physics. In quantum physics, that's not the case. We have to have complex numbers, and we have to live with complex numbers. So psi is unobservable, but what is psi? If you say psi, and this was one of the biggest mental roadblocks, there is so-called Born interpretation. Okay. So Born suggested psi itself is not observable, but if you take the modulus psi of x, y, and z, and t, and square it, this is observable, and he called this probability amplitude. Probability to find particle at x, y, z, and t. So the square is probability, then we call psi itself probability amplitude. Of course, this doesn't mean like for okay, here is like a probability amplitude. Let's say this is x, and this is psi, and I have something like this. And it doesn't mean like I have like a single electron and I just distributed the entire like real axis, and electron is part of electron is here, part of electron is there. We don't say that. So if we make a measurement, so we are going to find an electron here, right? Like we are going to say that the wave function collapses to this x is equal to x naught. But before, like prior to measurement, this electron is like a probability amplitude that could be anywhere. But it's not like, oh, part of charge is here, right? That's important to emphasize. But if you, like, for example, you measure the electron, you find this. If you keep the, like, if you repeat the experiment, like, I don't know, 100,000 times, you are going to reproduce this distribution. So that's the interpretation. So then the messages. So a wave has both amplitude and wavelength. So amplitude we describe by wave function psi, and wavelength is given by de Broglie relation. Lambda is equal to h over p. Good? Yes?
So simply you are saying that after thousands of experiments, electrons, you understood that distribution?
Yes.
And that is the second power of psi. So they arrived at this conclusion that psi is this.
Yes, psi is probability, right? Absolute value square of psi is probability to find electron at x, y, z, and t. Exactly like the probability you learn from like mathematics. But psi itself is amplitude, which is unobservable. There's no way you can reach a full wave function without taking its absolute value. Right? We cannot measure that. We don't know. So in some sense, we have incomplete information about the system.
So we believe it because of this, that probability, like the second power.
We blame it.
Believe it.
We believe it. Yes. That's yeah. I think as far as I know, yeah, that's first suggested by like de Broglie and then formalized by Schrödinger and Heisenberg, and that's the state after 100 years. Any questions or any comments? Yes.
Can we affect this amplitude probability and
The way the psi.
yeah, can we affect it?
I mean, you can of course change it, right? Like it has some value. For example, you can kick it exactly like you kick an electron, but the exact nature of the change you do is still unobservable. As soon as you do an observation, you collapse the wave function and you get this partial information. Not the entire, maybe, I don't know, psi is doing something crazy somewhere else, you cannot see that. Yes. Yes, wavelength we can observe. I'll come to this how we can, for example, for an electron, we can look at it from the de Broglie relation. There's nothing about that, right? Energy of the electron is going to give you the momentum, and momentum of electron is going to determine the wavelength.
Only for particles or, for example, for human bodies?
For like that's the power, right? That's the like more. That's the more extraordinary suggestion about this for everything. Even you right now is a wave. You are a wave, and your wavelength is like, if you remember, Planck constant is itself a very tiny number, and you divide this tiny number, which is really large momentum you have, because you have a very large mass. Then the wavelength you have right now is going to be, I don't know, 10 to minus 20. Textbooks calculate it, but the point is it's tiny, it's completely unobservable. But you can do like things like the interference experiments, which hopefully I will come to. And actually, if you do it right, even you can show interference. I don't know anyone doing it with humans yet, but we know interference with like very large atoms are possible. Yes.
Does the wave function has any units?
Yeah, that's a good point. The units, let's think about units. Suppose we are in one dimension, right? So what I know is like if I sum over all probabilities, it should be 1, right? If you sum over everything, you have 1. So let's sum over everything. So this psi of x squared. So for this to be 1, right? This is length. This should be 1 over length, because 1 is, last time I checked, has no units. Then psi square should be 1 over length, and psi should be, okay, 1 over maybe L to the 1/2. That's the unit. That's a good point. Thank you. Any questions or comments? So let's think about description of a wave. Okay. Okay, I cannot spell. I mean mathematical description. Let's think about the simplest wave. Simplest wave is like, let me think about this y-axis to be the wave oscillations, and x-axis is something like that. This is x, and I think at a given frozen time I have something like that. I can describe this y of x comma t as I don't know, it can be anything, a cosine omega t minus kx. So this is, yeah, I think, first of all, I think maybe you are more familiar with showing frequency with f in high school. I think you should check, but f and mu are the same. I think I'm more familiar with mu, but sometimes I may use f. But there's also so-called angular frequency. So angular frequency, omega is related to nu by this relation 2 pi nu. And there's, okay, you are familiar with wavelength, right? So lambda is wavelength. There's also wave number, and we use k for that, is 2 pi over lambda. Unfortunately, these are confusing. I think easiest thing you can do is to just memorize, right? But if you keep using it, at some point it becomes like a muscle memory. So in 3D, for example, in 3D, k is going to be kx, ky, kz, and x is going to be x, y, and z. Then kx, I defined there, is going to be replaced by k dot x, and you can see this is going to be kx times x plus ky times y plus kz times z.
So wave number is how many waves inside one cycle?
I am not sure if that's true, but it's just wave number is like 1 over wavelength. 2 pi, right? 2 pi times. I don't think it's like counting how many. I don't think that's like I think in physics we have to live with terrible terminology, and my suggestion is do not try to get something from the names. People are going to give them terrible names to things that will only confuse you. Just take what it is and just try to like have your own mental map if you want.
Yeah, sometimes understanding the mathematical relation is hard as well.
Yeah, I think terminology will pollute the physics, right? I think this will always be the case. Do not focus on names. So okay, what we need to be careful is like matter waves. Matter waves are packets of waves. What this means is like usually you can think about wave like this, right? That oscillates back and forth from minus infinity to plus infinity. But in the case of matter waves, we have like something localized, I don't know, like a blob of object, which could be photon or could be electron, it could be atom, and we are imagining inside this object there's like some oscillations, and this thing is called wave packet. Good. And what you can see from this wave packet, and different waves, like they just come together inside the packet, right? For example, the wavelength here is not same as wavelength here, right? You superimpose multiple wavelengths, multiple wave numbers, and multiple frequencies in the same window. So you need to like take superposition of different frequency and wavelength components, and let's do that. So we need to superimpose different lambda and different omega. And to understand that, let's do the simplest thing we can imagine. Let's say there's like one wave which is, okay, I just did this for like a toy demonstration. It doesn't have to be this. Cosine omega, there's like some, I pick some omega, a little bit above this omega, I call it delta omega times t. And also I pick some k, a little bit above this delta k and x, and this is still a one-dimensional wave. And I copy this And the reason I do this, you are going to see it was a little easier to calculate like this. I don't want to deal with too many cosines and sines. This is 2, and I want to like do this and do this. Okay. So if you want in the frequency spectrum, like you can see, right, any signal, you can take the, right, you can decompose it in its frequencies, and you just, in my case, there are only 2 frequency components, omega plus delta omega and omega minus delta omega. Is that clear? Like if you want, I'm just taking one wave, maybe color red, another wave, okay, another wave, okay, something like that. And what you are going to see is like there will be 2 oscillations. There will be like one envelope, maybe I can use green for that. There will be like one envelope, and inside this envelope you are going to oscillate like this. Yes. So like I'm trying to just, if you like take these 2, you know Python, right? In the Python, choose omega, choose delta omega, and plot y1 and plot y2. What you are going to see is like this. Like, okay, let me erase this. You are going to see, okay, this is terrible, I apologize. So there will be like a small, okay, I cannot draw because this is not very precise, something like that, and then it is going to grow again, and then it's going to grow again. So what I'm trying to say is like there's like an amplitude here, there's like an amplitude here, and there's like an amplitude here. Because there are 2 frequencies, right? There are 2 different wavelengths you overlap. I think the best thing you can do is just put this in Python and plot it. You are going to see what I mean. And you play with omega and k, and you'll see. Now I want to calculate this object. Let's calculate y1 plus y2 is equal to. So this is a cosine, let me call this entire thing cosine theta 1 plus cosine theta 2. And here I am going to use this property of cosine. It can be written as 2a cosine, I think theta 1 plus theta 2 over 2 times cosine theta 1 minus theta 2 over 2. I think everybody's familiar with this formula, right? This is generic, hopefully I'm not doing any trick. And okay, theta 1, theta 2, they are like depend on omega and delta omega, k and delta k. So if you do this, their sum is right, this one is this plus this, 2 omega divided by 2 is going to give me 2 amplitude omega t minus kx. So this is the first one, and cosine, the second one is going to give delta omega t minus delta k x. I think this is a little bit more representative, right? I didn't do anything. I just took these 2 waves. I just take these 2 waves, I use cosine, and I came up with this last expression, which is this one. And you can kind of see both oscillations in the same function. Hopefully that's a little bit clearer. So what you need to see is there are like fast oscillations. There's like fast oscillations. With so-called, let me define so-called phase velocity, which is going to be omega over k. And there are like small is not slow oscillations with group velocity delta omega over delta k. right? I just take this one and I just take this one. But as delta omega and delta k go to 0, this is going to be a derivative, and this is going to be delta omega d omega over dk. So that's the group velocity. Right? And this is like, let me also call something called dispersion. This is like omega depending on k is called dispersion because different wavelengths, different k, propagate with different velocities. Good. Any questions? A little bit of terminology, hopefully not too much. And maybe I can give you an example and then finish the class there. Here's the example. Let's calculate group velocity. Let's calculate Vp and Vg for a relativistic electron. So what this means is, like, first, for a relativistic electron, we know energy is equal to gamma mc squared, momentum is equal to gamma mv. We know about these things. And from Planck relation, E is equal to h nu. Then nu is equal to E over h, which is equal to gamma mc squared divided by h. Then omega is equal to 2 pi nu, which is going to be 2 pi over h gamma mc squared. And I also need to calculate k. To calculate k, I need to calculate lambda. Okay, this is Planck, and this is h over p. This is de Broglie, and then this is going to be h over gamma mv. Then k is equal to 2 pi over lambda, which is going to be equal to 2 pi over h gamma mv. Hopefully that's clear. I'm just reusing the definitions we had. Let's first calculate the phase velocity, 1, which is easier. Phase velocity, Vp is equal to omega over k. I think my omega is, let me copy. So this is my omega. So this is my k. And I divide these two things. Cancel this with this, cancel that with that, this, and that. You can see this is equal to C over V times C. Because V is always less than C and C over V is bigger than 1, something bigger than 1 times C is bigger than 1, so we can see phase velocity is bigger than C. So this is not physical. So phase velocity is not physical. We didn't expect it to be like physical anyways, right? We are like if you look at that in the here, right? This is the envelope itself. We care about like these individual waves, right? Like you are not probing this envelope. At any moment here, you want group velocity to be physical, which is supposed to be less than. But the gigantic wave itself can do something crazy. We don't have access to that. So let's also calculate group velocity. So group velocity. So for this, we need to take derivatives, and where we have square roots. It's going to take a few minutes. Hopefully you help me. I noticed that like I do sometimes mistakes and people don't fix it. It's not on me. It's your responsibility for anything I do wrong. Please help me, and if I do something silly, please fix it. I'm not very good at derivatives. So let's do this. Vg is equal to d omega dk, but what we saw above is like both omega and k, we obtain it in terms of v. So it would be nicer to take derivatives in terms of d omega dv and dv dk. So I use chain rule here. Okay? So let's calculate d omega dv is equal to d over dv. Let me copy omega I just derived here. Okay, it's this entire thing. And I need to take the derivative by knowing that this is gamma is equal to 1 over root 1 minus v squared over c squared is going to be equal to 2 pi over h and c squared minus a half 1 over 1 minus v square over c square 3 half minus 2v. Okay, my v is a little bit ugly, sorry about that. V over c squared and parentheses, right? So this is equal to, okay, this one is going to cancel this. So this c square is going to cancel this. The end I have 2 pi over h and v. Actually, let me write it like gamma cube mv. Any objections? Let me check. 2 pi over h gamma cube. Yeah, I got it right. This is like unbelievable. Now I want to calculate dk dv is equal to d over dv. Let me copy k I derived here. This is maybe this one. And now you can see there are like two v's. There's v inside gamma and there's v inside v. So the first one is 2 pi over h 1 over 1 minus v squared over c squared cube and minus a half and yes. Yes, I will come to that. So I will find dv over dk, but dv dk is much harder. So I'm going to use dk dv, and I'm going to use dv dk is equal to 1 over dk dv. That's a very good point. Thank you pointing it out. If you try to calculate this, you'll see you have to invert it, right? K is written in terms of v, and writing like it's like a quadratic equation. You can do it, but this one is a little simpler. Good point. Thank you. So this one is minus 2v over c squared times mv, and there's also second one plus 2 pi over h gamma times m. So this thing is equal to, okay, again this to cancel with this. And what I did is like I want to take it inside the parentheses, 2 pi over h gamma mv, and this is going to be equal to first from here this is 1, and the second one is going to give me plus. Okay, there is v here, there's v here, this is v squared over c squared. There is like gamma squared here, this is going to be 1 minus v squared over c squared, and close the parentheses. Is that clear? And this is 1 minus v squared over c squared plus v squared over c squared, 1 minus v squared over c squared, cancel that with that, and this is going to be gamma squared, right? At the end we have 2 pi over h gamma cube mv. Lastly, let's come to group velocity, which is the omega dk. Okay, we said it is like dv times 1 over dk dv. Yes. 1 or 1 over v. Oh, there is no v term in the second. So here, so this one is okay. This one is just the inside the parentheses. It is 1 over 1 minus v square over c square, right? So this entire object is 1 over 1 minus v square over c square, but we wrote it like a gamma squared. Oh, there is like 1 over v. So I took inside the parentheses for this, right? This is 1, right? The second term is 1, right? I take 2 pi over h gamma mv, this is 1, plus anything that remains here is like v square over c square, which comes from v square and c square, and there is nothing else, right?
Well, was gamma cube there?
Gamma cube? Here, gamma cube is here.
Yeah.
And I took it out as, oh, I see. So, no, I took it out as like gamma. There is 1, this one is coming from the second term, this is coming from the first term. In the second term there is v here and there is v here, v squared. And there is this c squared here. I mean, yes, I wrote the first term and then second term. I apologize. Because this was easier to write, I just 1 plus and focus on the hard part.
And they're saying in the first term that that term doesn't include v.
Yes, because I take derivative with respect to v, right? If you take the derivative with respect to, okay, keep this part, take the derivative with respect to v, derivative of v with respect to v is 1.
Hocam parantezi dağıtırsanız ona v gelmiyor zaten. Bir alt satırda biri böyle bir şey alacak.
Oh, I see, this one, like that, I see. Now I see, right? 2 pi gamma m, right? 1, okay. Now I think I see. You are right. Good? Happy? Good, okay. So then this is 2 pi over h. I think this is like that. I see. Yes, I think my note is also like that. Good job. Wonderful. It took a while for me to get there, but I appreciate. So this one is, let me copy these results, not to write the whole thing again. So this one is the first one. Yeah, sometimes I talk and write, it's really hard to see. And I don't see what I write myself. I apologize for that. Hopefully you can try sometimes and see how hard. And I have to use this terrible tablet. I am doing like many challenges for myself. But this is 1 over like that. Maybe I can try to make it a little bit down. There is 1 hour. Now this is my favorite part. Let's hope everything will cancel. So this is 2 pi are gone, gamma cube are gone, m is gone, m is gone. So at the end, what we have is V group is V, which is the physical velocity of electron. Okay, this is good news. So we don't have anything more than speed of light. Any questions? Yes. So the phase velocity is like meaningless. Like I said, it is like this entire envelope is doing something, and it turns out to be bigger than speed of light, but we don't care about that. What's that? Not really. So can you hold just 2 minutes? I have one more thing, I promise, and then I will finish very quickly. So maybe just the experiment in 1 minute, and then you can think about it yourself. Okay, maybe you are already prepared. Let me do it next time. Thank you.